You ever stop and wonder how your phone can juggle a dozen open apps without breaking a sweat? Or how your computer can find that one file you saved like a year ago in a split second? Well, it's not magic. It's all about organization. And today, we're going to pull back the curtain on three of the most important ways programs keep information straight: stacks, queues, and decks.
So yeah, how do they keep track of everything? The secret is something called data structures. The best way to think about them is like super specialized storage closets. You know, you've got one for your clothes, one for your tools. Each one is built for a specific job, which makes putting stuff in, finding it, and taking it out as fast and easy as possible.
All right, here's the plan. First, we're going to meet the stack. Then, we'll get in line with the queue. After that, we'll check out their super flexible cousin, the deck. And to wrap it all up, we're going to put what we learned to the test with a classic coding puzzle I like to call the bracket challenge. Let's get into it. Okay, our first stop is the stack. And really, its whole identity is built on one simple but super powerful idea: last in, first out. And honestly, the best way to get this is to just picture a stack of pancakes, right? You make one, you put it on the plate. You make another, you put it on top of that one. And when it's time to eat, where do you take from? The top. The last one you put on is the first one you take off. You can't just yank one out from the middle, you'd have a total mess. So that brings us to the official definition. A stack is just a collection of stuff where you can only add and remove items from one end, what we call the top. This creates that last in, first out behavior. And for short, we call it LIFO. Just remember, last in, first out. So how does this actually work in the code? Well, a really common way to build a stack is just with a basic list or an array. All you do is keep track of where the top is. When you want to add an item, we call that a push. You just stick it on the end. And when you want to take one off, that's a pop. You just grab it from that same end. That's it. Because you're only ever dealing with the very end of the list, these operations are incredibly fast, super efficient. Next up, we've got the queue. Now, if the stack's whole deal was last in, first out, the queue is its polar opposite. Its rule is first in, first out. And the analogy here is something you do like every day. Just picture people waiting in line, a queue, for coffee. The first person to get there is the first person who gets their latte. It's fair, it's orderly, and that is exactly how a queue data structure works. So the formal definition is this. A queue is a collection where you add things to one end, the back, and you take things away from the other end, the front. This system guarantees that first in, first out principle, or FIFO for short. The first thing you put in is the first thing you get out. Okay, so let's put them side by side to really lock this in. A stack is like pancakes, LIFO, last in, first out. A queue is like a line, FIFO, first in, first out. If you can just remember those two simple analogies, you'll never get them mixed up. But there's a little catch when you try to build a queue with a standard array. Think about it. As people get served and leave the front of the line, you get all these empty spots opening up at the beginning. So what happens when new people keep joining and the line hits the physical end of your array, even though you've got all that empty space back at the start? The solution is it's so clever. It's called a circular array. Basically, we pretend that the end of the list connects right back to the beginning. It wraps around. So when you get to the last slot, the very next spot you fill is the first empty one at the very start. This way, we just keep reusing the empty spaces and we never waste any room. Brilliant. So we have the super strict LIFO stack and the super strict FIFO queue. But what if you need more? More power, more flexibility? Well, that's where the Deque comes in. It's pretty much the best of both worlds. A deck queue, and that's short for double-ended queue, is basically a queue on steroids. It's a collection where you have the total freedom to add or remove items from either the front or the back. This gives you four main moves: add to the front, remove from the front, add to the back, and remove from the back. And think about what that means. If you decide to only use add to back and remove from back, well, you've just made a stack. If you only use add to back and remove from front, boom, you've got a queue. It's the ultimate flexible tool. All right, that's enough theory. It's time to see why any of this actually matters in the real world. We are going to tackle a classic programming problem, the bracket challenge, and we're going to do it by putting our friend the stack to work. So here's the puzzle. How can we write a program to check if a string of different brackets is balanced? What that means is, does every single opening bracket have a matching closing bracket in the right spot? Now, your first instinct might be to come up with all these complicated rules and counters to keep track of everything. But it turns out there's a beautifully simple way to do this. The perfect tool for this job is a stack. And here it is. This is the aha moment. Just watch how the stack makes this problem trivial. We're going to read the string one character at a time. First step, an opening parenthesis. Okay, we push it onto our stack. Next, an opening square bracket. We push that right on top. Now what do we see? A closing square bracket. So we peek at the top of our stack. Is it a match? Yes, it's an opening square bracket, so we just pop it off. It's gone. Finally, we see a closing parenthesis. We check the top of the stack again. It's an opening parenthesis, a perfect match. We pop it off. Now we're at the end of the string, and our stack is completely empty. That's it. That's how we know for sure that the brackets are balanced.
And that right there is the big takeaway. Choosing the right data structure is like a superpower. It can take a problem that seems really complex and messy, and it can make the solution just clean, simple, and elegant. So I'll leave you with this one last thing to chew on. What in your daily life actually works like a stack or a queue? I mean, think about the undo button in your text editor, or a line of cars at a red light. Once you start looking for them, you start seeing these simple, powerful ideas absolutely everywhere.